Welcome back to the Deep Dive. Today, we are tackling something that I think most of us take for granted until we absolutely desperately need it.
Oh, for sure.
We are talking about the ability to turn off pain, but not just knocking you out with a sledgehammer. We're talking about the sniper approach. Precision.
It is a fascinating distinction. In previous discussions, we've looked at general anesthesia, which is essentially a controlled coma.
Right.
It shuts down the entire system, consciousness, reflexes, your drive to breathe. But today, we are looking at Pharma 22.
Pharma 22. That sounds like a secret Area 51 project. Or maybe a Taylor Swift song about drugs.
I wish.
Yeah.
No, it refers to the chapter alignments in our source materials, specifically dealing with local anesthetics.
Of course.
And we are synthesizing two absolute Bibles of pharmacology here. We have Ketsung and Trevor's Basic and Clinical Pharmacology, specifically their chapter on this, which gives us this beautiful clinical scaffolding.
How to.
The how-to, the organization, the practical application. And we are pairing it with Goodman and Gilman's The Pharmacological Basis of Therapeutics, which is that it's the deep molecular, almost quantum level reasoning.
So Ketsung is the user's manual, and Goodman and Gilman is the why on earth does this even work? Engineering schematic.
That is a fair way to frame it. And the core tension we are exploring today is exactly what you hinted at. How do we take a human body, which is essentially a massive grid of electrical wiring, constantly screaming information to the brain, and silence just one specific wire without cutting it?
Right.
And maybe more importantly, how do we ensure that silence stays local and doesn't leak out and, crash the main computer, the heart and the brain?
It's the difference between turning off the light switch in the kitchen versus cutting the power line to the whole city.
Precisely. And the stakes are high.
Yeah.
If you mess up general anesthesia, the patient might wake up, or they might never wake up.
Both terrible outcomes.
Both terrible. But if you mess up local anesthesia, you might have a patient who is fully awake staring at you while their heart stops beating because the drug migrated to the wrong place.
Okay, that is a terrifying image to start with.
Yeah.
But before we dive into the molecular nitty-gritty, we should probably put out our standard disclaimer.
Yes, definitely.
We are building a conceptual map here. We are synthesizing these texts to prepare your mind, but this is not a substitute for actually reading the chapters.
Not at all.
So don't go sticking needles in your friends based on this deep dive.
Please don't. These drugs are tools of immense precision, but you have to remember at their core, they're also toxins. In fact, that's where they come from. The history here is rooted in toxins and plant extracts.
So what is our mission today? If you, the listener, stick with us for the next hour or so, what is the mental model you're going to walk away with?
We have 4 pillars for this. First, the mechanism. We need to understand why this drug has to work from the inside of the cell, not the outside. It's an inside job.
An inside job. I like that.
Second is selectivity. Why does the pain stop before your ability to move? Why can you feel pressure but not the cut?
Which is always the scariest thing when a doctor says, you'll feel some pressure. I'm immediately thinking, what does that mean?
Exactly. We will explain the physics behind that feeling. Third is chemistry. This is crucial. We'll explain why an infection like a hot abscessed tooth can chemically ruin the drug's ability to work.
So it's not just in my head when the dentist can't get it numb.
Not at all. It's pure chemistry working against you. And finally, safety. The sequence of toxicity, why the brain freaks out before the heart stops, and the lipid sink rescue that, frankly, changed the game in emergency medicine.
Okay, let's unpack this. I want to start with the molecule itself. You mentioned in the notes that chemistry is destiny here. I remember looking at the diagrams in Goodman and Gilman, and these molecules look like, well, they look like they have a head, a body, and a tail.
That is the perfect way to visualize it. Every single effective local anesthetic molecule is built on this specific tripartite structure. It's like a bridge connecting 2 different worlds.
Okay. On one side, you have the head. This is an aromatic ring.
An aromatic in chemistry doesn't mean it smells good, though I guess cocaine probably has a smell.
It does. But in this context, aromatic refers to the benzene ring structure. What matters for us is that this part of the molecule is lipophilic.
Lipophilic, meaning fat-loving.
Fat-loving. It hates water. This aromatic ring is what allows the drug to slide into the fatty membrane of the nerve cell. If you don't have this lipophilic head, the drug just bounces off the nerve sheath. It can't get in.
So the head is the ticket into the club. It's the VIP pass that lets you through the velvet rope of the cell membrane.
Correct. And the degree of lipophilicity matters immensely. The more lipophilic that head is, the more potent the drug is.
Why is that? Why does loving fat more make it stronger?
Because nerve membranes are essentially layers of fat. A drug that loves fat will rush into that membrane and, crucially, it doesn't want to leave.
It's comfortable there. Very. It creates what we call a depot effect right there within the membrane. So high lipophilicity equals high potency and usually a longer duration of action because it hangs around for longer.
So a drug like bupivacaine, which is a real heavy hitter that lasts for hours, it must have a very, very fat-loving head.
Exactly. It's extremely lipophilic, which is both its greatest strength and, as we'll see later, its greatest weakness.
Okay, interesting. So that's the head. What's on the other side?
On the other end, you have the tail. This is typically an imashimine group, and it's the polar opposite. It's hydrophilic. It loves water.
Hold on. Why do we need it to love water? I thought we just said it needs to get into the fat of the nerve.
Because it has to get to the nerve first. Think about the journey. You inject the drug into the tissue. It has to diffuse through the extracellular fluid. And what is extracellular fluid made of?
Water. Mostly water.
Exactly. If the molecule was 100% fat-loving, like a drop of oil, it wouldn't diffuse. It would just sit there in a globule or get stuck in the first piece of fat it touched. It wouldn't travel.
So it needs to be water-soluble to travel through the watery environment of the body, just to reach the nerve in the first place.
You've got it. It's a hybrid. It's an amphibian. It needs that water-loving tail to swim through the tissue to the nerve.
A fat-loving head to enter the nerve, and a water-loving tail to swim to the nerve. I like that.
That's a great analogy. The technical term is amphipathic, but amphibian works just as well. And connecting these two opposing personalities is the body or the linker.
The bridge between them.
The bridge. It's an intermediate chain. And this little chain, this body, is what determines the entire class of the drug. It's either an ester link or an amide link.
Esters and amides. I see these terms all the time. But honestly, in the real world, what is the practical difference? Why do I care if it's an ester or an amide?
You care immensely. You care because of how your body destroys them. This is all about metabolism and stability, which in turn dictates duration and even side effects.
Okay, so let's break it down. Let's start with the esters.
Esters are the OG anesthetics. The old school. Think Procaine, which was marketed as Novocaine, Tetracaine, and of course the grandfather of them all, cocaine.
Cocaine is an ester.
It is. The ester linkage involves a carbon-oxygen bond. Chemically, it's fragile. It's the self-destruct button of the molecule.
A built-in weak point.
A very weak point. The moment an ester anesthetic hits your blood, it runs into an army of enzymes called plasma pseudocholinesterases.
That's a mouthful.
It is, but they are incredibly efficient. They see that ester link and snip, they hydrolyze it, they add a molecule of water across that bond, and the whole drug molecule just falls apart.
And this happens in the blood itself.
Instantly. In the plasma. This happens incredibly fast.
So esters don't last long at all.
Very short duration. This is why the old Novocaine or Procaine wore off so fast. You'd be in the dentist's chair, and 20 minutes later, you're feeling the drill again because your blood has literally eaten the drug.
But there's a darker side to esters too, right? I recall something about allergies from the reading.
Yes, this is a critical clinical pearl. When that ester link snaps, the drug breaks down into metabolites. And one of those metabolites is a molecule called paba-para-aminobenzoic acid.
PABA. Isn't that in sunscreen? Or it used to be.
It used to be, yes. And it turns out that PABA is a massive allergen for a subset of the population. It triggers true Ig-mediated allergic reactions in a significant number of people.
So when patients say, I'm allergic to Novocaine, or I'm allergic to the dentist shot, they're usually talking about an ester allergy.
That's right. They aren't allergic to the numbing mechanism itself. They are allergic to the metabolic debris, the PABA that gets left behind after the drug is destroyed.
So the chemists looked at this and said, okay, we need a stronger chain, a more stable connection.
Yeah.
And we need something that doesn't turn into allergenic trash when it breaks down.
Enter the amides. In the 1940s, scientists synthesized lidocaine. It was a revolution. They replaced that fragile oxygen link with a nitrogen and amide link.
And nitrogen is tougher.
Oh, much tougher. It is the difference between a plastic zip tie and a steel cable. The plasma enzymes in the blood, the pseudocholinesterases, they just bounce right off it. They cannot break the amide bond.
So the drug survives its trip through the blood. Where does it go to get broken down then?
It has to circulate all the way to the liver. It relies on the hepatic CYP450 enzyme system to be metabolized, and this is a much slower, more deliberate process.
Which means they last longer. Lidocaine can last for hours, not minutes. But it also means if your liver is failing, you might be in trouble.
Precisely. That is the clinical trade-off. In a patient with severe liver failure or cirrhosis, the half-life of lidocaine skyrockets. You give a normal dose, but the body simply can't clear it. The drug level builds up and up.
And toxicity becomes a real, present danger.
A very real risk. So the bottom line is esters equal blood breakdown, short-acting, and an allergy risk from PABA.
Okay.
And amides equal liver breakdown, long-acting, and generally hypoallergenic.
Got it. That's a clear distinction.
Now, there is a brilliant memory anchor here that Katzing points out, and it's almost too simple to be true, but it works every single time. It's the 2 eyes rule.
I love these tricks. Lay it on me.
Look at the generic name of the drug. If it is an amide, it will have the letter I in the prefix before the sicane.
Okay.
So lidocaine, bupivacaine, ropivacaine, prelocaine, they all have an I in the first part of the name.
Wait, let me check. Lidocaine, L-I-D-O.
Oh.
There's an I, plus the I in cane. So that's 2 I's. Bupivacaine, B-U-P-I. Yep, 2 I's.
Exactly. 2 I's means it's an amide. Now look at the esters. Procaine, P-R-O-C-A-I-N-E, only 1 I.
Cocaine, only 1 I. Tetracaine, only 1 I.
Chloroprocaine, 1 I. It works every time. If you were staring at a vial in the ER and you can't remember if the patient with the liver failure can take it, count the I's. 2 I's, think liver.
That is incredibly helpful. Wow. Before we move off the molecule completely, I saw a note about handedness or isomers. Goodman and Gilman gets really deep into this, referencing the chirality of the molecule. Why does the shape matter if the chemical formula is the same?
This is stereochemistry, and it's a huge theme in modern pharmacology. Molecules can exist as mirror images of each other, just like your left and right hand.
Right.
They're made of the same components, thumb, fingers, palm, but you can't superimpose them. A left glove doesn't fit a right hand. We call these enantiomers.
And nature actually cares about this.
Yeah.
The body can tell the difference between a left and a right-handed molecule.
Nature is obsessed with this. Biological receptors are 3-dimensional structures. They are chiral environments. They are the gloves, and the drug is the hand. It turns out that for bupivacaine, the drug is synthesized as a racemic mixture, a 50-50 mix of the left-handed version, the S isomer, and the right-handed version, the R isomer.
Okay, so when you give bupivacaine, you're injecting both hands into the body.
Yes, and both hands work pretty well to stop pain, but the R isomer, the right hand, has a sinister side. It fits perfectly, almost magnetically, into the sodium channels of the heart.
Oh, that's not good.
It's very bad. It binds to the cardiac channels and refuses to let go. This is the molecular basis that makes the racemic mixture of bupivacaine notoriously cardiotoxic.
So what was the solution?
Well, the pharmaceutical companies got smart. They figured out how to filter out the dangerous right hand.
You just kept the left hand.
Exactly. They developed a process to isolate just the S isomer, and that gave us the drug levobupivacaine. Levo meaning left.
Okay.
Or, in another case, they designed a new molecule from scratch, ropivacaine, which is purely the S enantiomer. It's built to be only left-handed from the start.
So ropivacaine is basically the safe left-handed cousin of bupivacaine.
That is a great way to put it. Ropivacaine gives you the same quality of sensory block, that same long duration, but because it lacks that right-hand shape, it doesn't stick to the heart as aggressively. You have a much wider safety margin.
It's pharmacology evolving from a blunt instrument to a precision tool.
Exactly. It's rational drug design.
Okay, so we have our molecule. It's got a fat-loving head, a water-loving tail, and a tough amide body. We've injected it near a nerve. Now we get to the mission impossible part, the mechanism of action. How does it actually stop the pain?
To understand this, we have to visualize the target. And the target is the voltage-gated sodium channel on the nerve membrane.
The Na+ channel. This is the wire. This is the thing that carries the electrical signal.
Right. Remember, a nerve signal, what we call an action potential, is just a wave of sodium rushing into the cell. Sodium is a positively charged ion. The inside of the cell is negatively charged at rest.
So there's a gradient.
A huge electrical gradient. When the channel opens, sodium rushes in, the voltage inside the cell spikes from negative to positive, and boom, the signal fires and travels down the nerve.
The goal of the local anesthetic is simple then.
Yeah.
Block that channel. Plug the hole.
If sodium can't get in, the membrane cannot depolarize. The signal can't fire. No signal, no pain. It's a dead wire.
Seems straightforward enough.
But here is the paradox, and this is the part that blows people's minds when they first learn it in Goodman and Gilman. We call it the guarded receptor hypothesis.
Okay.
The binding site for the drug, the keyhole where it locks the door, is inside the channel pore. But it is only accessible from the intracellular side, from inside the cell.
Wait, hang on. So the drug is floating around outside the nerve, in the tissue where we injected it, but the lock it needs to get to is on the inside.
Yes. The drug cannot simply plug the hole from the outside like a cork in a wine bottle.
That seems like a design flaw.
It's a huge obstacle. That's actually how tetrodotoxin, the pufferfish poison, works. It plugs the channel from the outside. But lidocaine... No. Lidocaine has to cross the membrane, enter the cytoplasm of the cell, turn around, and then plug the channel from the inside.
It's a Trojan horse mechanism. It can't just attack the wall. It has to infiltrate the city first.
Perfect analogy. It has to get inside to do its work.
This brings us to that pH puzzle you mentioned in the intro, the Henderson-Hasselbalch equation. I remember sweating over this in chemistry class, and I thought I had left it behind for good. Why does it matter here?
It matters more here than almost anywhere else in pharmacology. It's because of that head and tail structure we talked about, specifically the amine tail.
The water-loving part.
Right. That amine group can either have a hydrogen ion attached to it or not. When it has the hydrogen, it has a positive charge. It's a cation. When it doesn't, it's neutral. It's an uncharged base.
Okay, charged or uncharged?
In the bottle and in your body, the drug exists in both states at once, constantly flipping back and forth in a chemical equilibrium.
So you have two versions of the drug floating around.
You do.
Yeah.
Version 1 is the uncharged base.
Yeah.
It's neutral. Because it's neutral, it is lipophilic, it's fat-loving. This is the ghost.
The ghost, okay.
It can walk right through the lipid membrane wall of the nerve. It's invisible to the membrane's polarity.
So the ghost walks through the wall into the cell. That's step one.
Right. But here's the catch. A ghost can't turn a key. A ghost has no substance. To bind to the receptor inside the sodium channel, the drug needs a charge. It needs to be the cation, the positively charged form.
Solid form.
The solid form. We can call it the key. So the ghost gets in, but it can't do anything. The key can do the job, but it can't get in.
So how does this work?
It's a two-step process. Outside the cell, the ghost slips through the wall. Once it gets inside the cell, where the internal pH is a bit lower, it grabs a hydrogen ion from the water inside the cell and becomes the charged cation.
It solidifies.
It becomes the key. Now it's active. Now it can swim over to the sodium channel from the inside and lock it shut.
So it needs to be uncharged to get in, but charged to work. It's a shapeshifter.
Exactly. It's this incredibly delicate balance. And here's where we need to look at the numbers. Most local anesthetics are weak bases, with a pK somewhere around 8 or 9.
And pK, just to refresh, is the pH at which 50% of the drug is charged and 50% is uncharged.
Perfect. So let's take a drug with a pKa of 8.0. The body's normal tissue pH is about 7.4.
So the environment is slightly more acidic than the drug's 50-50 point.
It is, and the Henderson-Hasselbalch math dictates that the acidic environment will push the equilibrium towards the charged state. In fact, at normal body pH, about 80 to 90% of the drug is in the charged scucation form, the key form.
Wait a minute. So 90% of the drug we inject in the syringe is the key, not the ghost.
Correct.
But we just said the key can't get through the wall.
You see the problem. You spot the inefficiency. We are injecting a solution where only a tiny fraction, maybe 10 to 20% of the molecules, are actually capable of entering the nerve at any given moment. We are relying on that tiny minority of ghosts to slip through.
That feels incredibly inefficient. It's like sending an army to the gate, but only 10% of the soldiers have the password to get in.
It is. But here is the magic of equilibrium. As soon as those ghosts slip inside the nerve, the balance outside is disrupted. So some of the keys outside shed their proton and become new ghosts to restore the ratio.
Ah, Le Chatelier's principle. The system shifts to replace what was lost. So it's a continuous conveyor belt. Ghosts go in, and the keys outside turn into new ghosts.
Precisely. It's a slow but steady process. But now, imagine you disrupt that balance. Think about it: an infected wound, an abscessed tooth, a hot, red, inflamed cyst. What is the chemistry of pus and inflammation?
Inflammation implies acidosis, right? A low pH. It's acidic.
Very acidic. The pH in an infected tooth can drop to 5.0 or 6.0. Now do the math. If the tissue pH is 6 and the drug's pKa is 8, that gap is huge.
The environment is way, way more acidic.
So the equilibrium gets pushed almost entirely to one side. The amount of uncharged ghosts drops from 10% down to maybe 0.1%, maybe even less. You essentially zero ghosts.
So 99.9% of your drug is locked in the charged state. It's all keys, no ghosts.
Exactly. The drug is trapped outside the nerve. This is called ion trapping. The charged molecules bounce off the nerve membrane. They cannot penetrate.
That is why the dentist can give you 3 shots of lidocaine for a bad tooth, and you're still jumping out of the chair. It's not that the drug is broken, the environment is wrong.
The drug works fine, but it's shouting at the wall and can't get in. And the clinical trick to fix this is pure chemistry. You can buffer the solution.
What do you mean?
You add a little sodium bicarbonate baking soda to the syringe of lidocaine just before you inject it.
You're raising the pH of the solution itself.
You make it more alkaline. This forces the equilibrium to shift, creating more of the ghost form, the uncharged base. More ghosts appear. They rush into the nerve. Once they are inside, the cell's internal pH turns them back into keys and boom, instant numbness.
So you can actually speed up the onset of the block.
You can, even in non-infected tissue. It's a common trick in anesthesia. It's applied physical chemistry saving the day.
That is so cool. It's like hacking the system.
It really is.
So, okay. We've used our chemical trickery, we've gotten inside the nerve, we've turned into the key, and we've plugged the channel. But you mentioned something called state-dependent blockade. This sounds like the drug has a preference for when it works.
It absolutely does. And this is the secret to why local anesthetics are so exquisitely effective at stopping pain specifically. The sodium channel isn't a static hole. It's a dynamic machine with moving parts. It has 3 main conformational states.
3 states, okay.
First, the resting state. The channel is closed, but it's ready to fire. It's cocked and loaded. Second is the open or active state. The gate is open, sodium is rushing in. This is during the action potential.
And the third?
The inactivated state. After it fires, the channel closes again, but in a different way. It's closed and tired. It has to recover before it can enter the resting state again.
Resting, open, inactivated. Got it.
Now, here's the key. The local anesthetic molecule is remarkably bad at binding to the resting channel. If a nerve is just sitting there doing nothing, the drug has a very hard time grabbing hold. It has low affinity.
It can't find a good handhold.
Exactly. However, the drug loves the open state and the inactivated state. It binds to those conformations with high affinity.
So the drug targets nerves that are active, nerves that are actually firing.
Yes. This is called use dependence or phasic block. The more a nerve fires, the more its channels are flashing open and inactivated. The drug sees these open doors and vulnerable states and slips in.
So let's apply that.
Think about a pain fiber. You've just smashed your thumb with a hammer. That nerve is firing at a very high frequency. It is screaming. It is opening its channels hundreds of times a second.
It's basically waving a giant flag saying, "Over here, come block me, my channels are wide open."
Exactly. It is inviting the drug in. It's like a revolving door at a busy department store. If the door is spinning constantly, it's very easy to jump in. If the door is locked shut at night, which is like the resting state, you can't get in.
So the drug blocks the active pain fibers much faster and deeper than it blocks, say, the quiet motor nerves that are just humming along in the background, telling your muscles to maintain tone.
Precisely. This creates a natural selectivity for high-frequency signals, which is exactly what pain is.
That is fascinating. So the pain itself actually accelerates the relief.
In a way, yes. The blockade builds up with every action potential. Each nerve impulse allows a few more drug molecules to find their binding site, deepening the block.
This transitions perfectly into the next segment, the order of silence, or what the books call differential blockade. Because as anyone who has had an epidural knows, you don't lose everything at once. It's a fade out.
It is a predictable sequence, and understanding it is vital for reassuring patients. But to understand it, we have to look at the anatomy of a nerve bundle. We often think of a nerve as a single wire. It's not. It's a cable, a massive bundle of different kinds of wires.
Like a transatlantic internet cable.
Exactly. You have the outer sheath, the epineurium. Inside that, you have smaller bundles called fascicles. And inside those are the actual individual nerve fibers. It's layers upon layers.
The where you inject matters.
It does. When you perform a nerve block, you are injecting the drug outside the main cable. The drug has to soak through that outer sheath and diffuse inward from the outside in.
Which means the fibers on the outside of the bundle get hit first.
Right. We call those the mantle fibers. The fibers deep in the center, the core fibers, they get hit last because it takes time for the drug to get there.
So geography matters.
Geography matters. And often the mantle fibers supply the more proximal structures, like your shoulders or thighs, and the core fibers supply the distal structures, like your fingers and toes. So sometimes you'll get numbness in your shoulder before you feel it in your hand.
That's so counterintuitive.
It is. But beyond that geography, the type of fiber is what really determines the order of loss. And the sequence is usually very predictable.
Okay, what's the order?
First to go is typically sympathetic transmission, the autonomic nerves. This is why a spinal anesthetic can cause blood pressure to drop. You've numbed the nerves that tell blood vessels to stay tight.
They relax, blood pressure falls.
Exactly. Second is temperature, usually cold before warm. Third is pain, specifically the fast, sharp, pinprick type of pain. Fourth is touch and deep pressure. And last to go is motor function, the ability to move.
So let's go back to that C-section scenario. The patient is on the table. The spinal is in. The surgeon makes the incision. The patient says, "I can feel you pushing on me," and panics, thinking it's not working.
This is a classic moment. And what's happening is that the patient feels pressure, which is a low-frequency signal carried by large A-beta fibers. But they can't feel the sharp cut of the scalpel, which is a high-frequency signal carried by smaller A-delta and C fibers.
So the anesthesia is working, it's just not blocking everything.
It's working exactly as we expect. The expert clinician anticipates this and says, you will feel pressure like someone pushing on your tummy, but you will not feel sharpness. You have to frame the sensation for them. It's physiology, not failure.
Why does this happen? Is this just about size?
Yeah.
Small wires get cut first.
That's the myth we need to debunk. For decades, textbooks said small fibers block first. And while there's some truth to it, it's not just about diameter. It's much more complex.
Okay, what else is at play?
We already talked about one factor, firing rate, use dependence. Pain fibers fire fast, so they are more susceptible. But the other big factor is myelination, the insulation around the nerve.
I thought myelin protected the nerve. That would make it harder to block.
It does protect it, but it also changes how the nerve fires. In a myelinated nerve, the signal doesn't flow smoothly, it hops. It jumps from one gap in the insulation to the next.
The nodes of Ranvier.
Exactly. The action potential only happens at these nodes. Now, to stop a myelinated nerve, you have to block at least 3 consecutive nodes. If you only block 1 or 2, the signal is strong enough to actually jump over the block nodes to the next one. It's remarkably resilient.
So you need a puddle of drug big enough to cover a certain length of the nerve, enough to knock out 3 nodes in a row.
Precisely. And in smaller myelinated fibers, like the A-delta pain fibers, the nodes are closer together. So a small volume of drug can easily cover the critical length of 3 nodes. In a huge motor nerve, the nodes are much farther apart. You need more drug and more time to soak a longer length of the nerve to silence it.
So it's a complex mix of size, insulation, node spacing, and firing rate.
It's a multivariable equation that gives us this beautiful, predictable differential blockade.
Let's move to the practical side.
Yeah.
How do we actually get these drugs into the body? We have different routes, and Kitsung outlines them nicely.
We do. We can start with the simplest, topical. Applying it to a surface, usually mucous membranes. Think benzocaine gel. We use this for numbing the gums before the needle or in sprays for sore throats.
Is that safe?
It can be risky. A word of warning here. Mucous membranes, like in the nose or throat, are incredibly vascular. They suck up the drug almost as fast as an IV injection. You have to be very careful with toxicity when spraying stuff into the nose for a procedure.
Okay. Then there's infiltration. This is what most people think of. Just injecting it right into the tissue.
The standard cut and stitch technique. You're soaking the nerve endings directly in the area you want to work on.
And you level up to nerve blocks. This is aiming for the trunk of the nerve, the main cable.
Right. This is for when you want to numb an entire region, like a brachial plexus block for arm surgery. You use an ultrasound to find the main cable bundle in the neck or armpit, and you soak it in local anesthetic.
And that turns off the whole limb.
The whole arm. It's cleaner, uses less drug overall than infiltrating an entire arm, and provides fantastic, long-lasting post-op pain relief.
And finally, the big guns. Neuraxial, spinals, and epidurals. I feel like people use these terms interchangeably, but they're not the same.
Not at all. They're very different anatomically and functionally. A spinal or a subarachnoid block uses a tiny pencil point needle that pierces the tough sac holding the spinal fluid. You inject a very small amount of drug, maybe 2 or 3 milliliters, directly into the cerebrospinal fluid. It mixes immediately with the naked spinal cord nerves. Boom. Profound numbness, very fast onset, very solid block.
And an epidural.
Epidural means on top of the dura. You use a larger needle, but you stop outside that tough sac. You don't pierce it. You inject a much larger volume of drug, maybe 15 or 20 milliliters, into the space outside the sac.
So the drug has to soak through.
The drug has to diffuse through the dura to reach the nerves. It takes longer to set up, maybe 10 to 20 minutes. But the huge advantage is you can leave a tiny plastic catheter in there and keep topping it up for hours or even days, like we do for women in labor.
So a spinal is a one-shot sniper round. An epidural is a slow-release soak with the option to redose.
That's a perfect way to describe it. And the danger, of course, is if you are trying to do an epidural, which requires that large 20 milliliter dose, and you accidentally puncture the dura and squirt all of that into the spinal fluid.
That's a massive overdose for the spinal space.
That is what we call a high spinal, or a total spinal. The numbness shoots all the way up to the neck. You paralyze the diaphragm. The patient stops breathing. Their blood pressure crashes. It's a full-blown emergency. This is why test doses are absolutely critical.
Speaking of additives, we talked about bicarbonate, but the most common thing added to lidocaine is epinephrine, adrenaline. Why would we add a stimulant to a numbing drug? It seems paradoxical.
We call it the chemical tourniquet. Here's the issue. Most local anesthetics, with the notable exception of cocaine, are vasodilators. They relax the blood vessels around the injection site.
Then that's a problem.
It's bad for two reasons. One, the increased blood flow washes the drug away from the nerve, so the numbing wears off faster. Two, that washed away drug goes directly into the systemic circulation, straight to the heart and brain, which increases the risk of toxicity.
So you add epinephrine to shrink the blood vessels.
Epinephrine is a powerful alpha-1 agonist. It's a vasoconstrictor. It clamps down the capillaries right at the injection site. This has three huge benefits.
What are they?
One, it traps the lidocaine there at the nerve, so it lasts much longer. It can double the duration of the block. Two, it reduces bleeding in the surgical field, which surgeons love. And three, it keeps the peak plasma levels of the anesthetic lower, so it's safer.
But there's a rule, right? The old saying, fingers, toes, penis, nose.
The old dogma. Never use epi in end artery areas. The fear was that you would clamp the vessels so hard that you'd cut off all blood supply and cause gangrene or tissue death in the fingertip.
Is that still the thinking?
It's being challenged. Katsung and a lot of modern literature, particularly from the plastic surgery world, are starting to show that this risk is overstated, especially if you use low concentrations. But for a generalist, most textbooks still advise caution. You don't want to be the one guy who turns a patient's finger black.
Fair enough. Okay, let's talk about the dark side. Toxicity. LA. Local anesthetic systemic toxicity. This is what keeps anesthesiologists up at night.
It is the nightmare scenario. It happens when absorption exceeds metabolism, or more commonly, you accidentally inject the main dose straight into a vein. The drug bypasses the tissues and goes straight to the heart and brain.
And it hits two systems, you said. The brain and the heart.
Right. And there's a classic progression. The brain usually goes first.
What does that look like?
Phase 1 is CNS excitation. This is another paradox. You'd think a drug that blocks nerves would quiet the brain down, but it does the opposite at first.
Why?
Remember, the brain has inhibitory neurons, the brakes, and excitatory neurons, the gas pedal. It turns out local anesthetics are slightly better at blocking the inhibitory neurons first.
So you cut the brake lines of the brain.
Exactly. The brain starts speeding out of control. The patient might get early warning signs. They might say, my lips feel tingly and numb, which is circumoral numbness. They get a metallic taste in their mouth. Ringing in the ears, tinnitus.
And if it progresses?
Then they start twitching, muscle fasciculations. Then full-blown tonic-clonic seizures. The brain is firing uncontrollably because the brakes are gone.
And if you don't stop it there?
Eventually, as the drug level climbs even higher, it blocks the excitatory pathways too, and the brain crashes. Coma, respiratory arrest, the patient stops breathing.
Okay, so that's the brain. What about the heart?
Phase 2 is cardiotoxicity. The heart is basically a big rhythmic muscle driven by sodium channels. If you block those channels, the heart slows down, the electrical conduction fails, you get arrhythmias, the blood pressure plummets.
Now, lidocaine is interesting, right? Because we use it as a heart medication.
We do. At low controlled doses, we actually use IV lidocaine as an antiarrhythmic to treat certain heart rhythm problems. But at high toxic doses, it stops the heart's ability to pump altogether.
But there's one drug that is the shark in the water here, the one everyone fears. Bupivacaine.
Bupivacaine is the notorious one, and it all comes back to its chemistry. It's highly lipophilic and very potent, and it has a unique interaction with the cardiac sodium channel.
What's the problem?
Lidocaine is a fast-in, fast-out drug. It blocks the channel, but it also lets go pretty quickly between heartbeats. Bupivacaine is different. It goes into the cardiac sodium channel, and it stays there. It dissociates very, very slowly. It essentially permanently disables a fraction of the heart's conduction system during the cardiac cycle.
It creates a block that is incredibly hard to resuscitate from.
We call it the stone heart. You can do CPR, you can shock the heart, you can give epinephrine, but the bupivacaine is physically stuck in the channel, preventing it from working. And terrifyingly, with bupivacaine, the cardiac arrest can happen at the same time as the seizures. You don't always get that early CNS warning.
So what do you do? If you've overdosed a patient with bupivacaine, their heart has stopped, and CPR isn't working. Is there an antidote?
For a long time, the answer was basically no. You just did CPR and hoped. But in the last couple of decades, we discovered lipid emulsion therapy, and the story of this discovery is just fascinating.
It wasn't from a big pharma lab.
Not at all. It came from a curious observation in an academic lab. A researcher named Dr. Guy Weinberg in the late 90s was studying cardiac metabolism in rats.
Rats and labs, a classic combination.
He noticed something strange. He was giving rats lethal doses of bupivacaine to study its effects. Their hearts had stopped, but he noticed that the rats who had high levels of circulating lipids, basically fat, in their blood, they lived.
The fat rats survived.
They didn't just survive, they required massive, massive doses to be killed. He had this incredible insight. He thought, wait a second, is the fat protecting the heart? So he took this idea to the medical community. If a patient is dying of anesthetic overdose, let's inject a bag of sterile soybean oil into their veins.
I can't imagine that went over well. Nurse, get me the salad dressing stat.
They laughed at him. It sounded insane. Injecting fat can cause fat embolisms. It's considered dangerous. But he persisted, and the animal data was undeniable. He proposed the lipid sink theory.
Which is the sponge concept.
Right. Think of the bloodstream as a hallway. Bupivacaine is the toxic assassin running through the hall looking for the heart muscle to bind to. Intralipid, which is basically sterile mayonnaise in an IV bag, is like rolling 1,000 sticky, fatty tumbleweeds into that hallway.
The assassin gets stuck to the tumbleweed.
Bupivacaine is intensely lipophilic. It loves fat. Given the choice between the protein of the heart muscle and a pure globule of soybean oil, it will preferentially jump off the heart and into the lipid globule. It is literally scrubbed from the plasma.
That is one of the most elegant mechanisms I've ever heard. You utilize the drug's greatest strength, its love of fat, as its own trap.
It's full circle chemistry, and it works. It has revived patients after 30, 40, even 60 minutes of dead-end CPR. It's nothing short of miraculous.
So let's bring it all home. We've gone from the aromatic ring of the molecule all the way to the lipid sink rescue. What is the big picture synthesis here? What's the core mental model?
The mental model is this. Local anesthetics are precision tools that exploit the state of the sodium channel. They work best on nerves that are active and screaming, which is use dependence.
Okay.
They require a chemical journey. They must be uncharged to enter the nerve, but charged to lock the door from the inside. And they carry distinct risks based entirely on where they end up. If they stay in the nerve, they are miracles. If they drift to the brain or heart, they are potent poisons.
And the margin between miracle and poison is anatomy, dosage, and technique.
And vigilance. Always, always vigilance.
Here's a thought to leave you with. We started this journey with coca leaves chewed by Andean natives for centuries. We moved to purifying cocaine, then synthesizing procaine, then the game-changing amides like lidocaine. Now we have optically purer, safer molecules like ropivacaine.
A clear evolution toward precision and safety.
But nature isn't done teaching us. You mentioned tetrodotoxin in the notes.
Yeah.
The pufferfish poison. TTX.
Ah, yes, TTX, the ultimate sodium channel blocker.
Lidocaine and all its cousins have to do this complicated Trojan horse trick, blocking the channel from the inside. But tetrodotoxin just plugs it from the outside. It's like putting a cork in the bottle from the top.
Yeah.
He's unbelievably potent, orders of magnitude more than our clinical drugs.
It is a true natural toxin.
So the question is, could the future of pain control be molecules that don't need to do the Trojan horse dance? Could we develop a drug that silences pain by blocking the channel from the outside? And maybe, because it never has to enter the cell, maybe it would never touch the heart or brain channels, a truly local anesthetic.
There is research happening right now on what are called Site-1 blockers, like neosaxitoxin, which work just like that. It's a brave new world out there. The quest for the perfect, absolutely selective silence continues.
I love it.
It's a fascinating field.
If you want to see the diagrams of the channel, which are honestly beautiful in their complexity, open up Goodman and Gilman, the chapter on local anesthetics. If you want the clinical dosages and the fingers and toes rules, hit Ketsung's chapter.
Reading them together really gives you the full picture.
Thanks for diving deep with us.
Until next time.